in the last class, the digital system design was introduced. We are discussing about the specification and the implementation of digital systems. Today we will see that what do we mean by implementation of digital system. Implementation means how the system is constructed from smaller and simpler components called modules. The modules can vary from simple gates to complex processes. That means that one system has a related components. We have defined digital system like that. Now, these components, again a set of components or more than one components that is clustered together, and we are calling that is as a module. And this module can be a set of gates, a combination of simple gates, or it can be a complex processor. Now, digital system follows some hierarchical implementation. So, today we will see that what do we mean by this hierarchy and how that one large digital system can be designed. First, we see that what do we mean by modular design. See, if we see first, we take one page and see that the way we have discussed that as if this is some function or behavior of the system, and some inputs are fed and outputs are taken. Now, if this will be a large if this is a large system, what we can do, we can break this thing as a some smaller blocks. Say this behavior as if this is some smaller blocks. Again it has each of the blocks has its own function. So, this is F1, F2. Function and behavior means that it is normally it is used the same definition. So, F5, X6, say these are the some blocks. That means, these as if this large system is broken into some smaller blocks. There must be some interconnection between these blocks. Okay. So, these each smaller blocks we are calling this is a module. So, mainly this is divide and conquer, means the large system is divided and then the smaller module is designed first. Modules are designed and built separately and then assembled to form the subsystem. Modules are designed and built separately, then assembled to form the subsystems. Why we are doing this thing? Because it simplifies the implementation and debugging. Because always it is true that instead of designing a large system, if I partition that thing into smaller blocks. Say I am partitioning in this way, and then first to design this module, say this is module 1, or design this module, say module 2, first it will be easier. Another thing is, if there is some problem, that means just to debug, if the full system is not working, if it does not work properly, then first we will identify that whether that each module, the smaller modules are working or not. Then it must be, instead of testing the whole system, or instead of debugging the whole system, the debugging of smaller modules are always much better, it is advantageous. Now, one of the major factors for the cost effectiveness of digital systems that comes from this modular design. Now, we see what do we mean by top down design approach. So, it starts at the top root and works down by successive refinement, and decomposes the system into subsystem, and then subsystem into simpler and smaller subsystems, and so on. When it will stop? Because what we are doing, one system first we are breaking or partitioning into smaller subsystems, then once subsystem again we are breaking that smaller subsystems. So, when we will stop? So, we will stop when subsystem can be realized by directly available module. So, these modules, what just now we have discussed, that module, that as if these modules are designed and built separately, and these are available to us. So, when we get this subsystem as the modules which are available, then we will stop that thing. So, this is top down design approach. Now, if we see pictorially, then say I have first one, say some I am taking that this is the system that I want to design. Okay. Now, top down approach means as if these are in the second level, say as if these are some blocks, say some smaller subsystems, these are smaller subsystem. These are smaller subsystems. Now, say each block, say this is number of subsystems are there. Now, as if these modules again partition into some smaller modules which are actually realized by some gates, logic gates. Okay. These are by logic gates. Then again these gates, this is a set of gates. Say this is S1, S2, S3. Then this S1 is again partitioned into say some transistors. Okay. So, these are a combination or set of, say a set of transistors, say T1, T2, T3, T4. So, why it is called top down? As if the for this system, this is first we have, it is coming from this direction, it is partitioned. into subsystems. Then say this subsystem, only this one is broken as a group of smaller subsystem which consists of a number of gates. Now, again say it is coming from that here we are getting that a number of, as if smaller, it is again partitioned into smaller sub blocks, and these are nothing but a set of transistors, set of transistors. These are transistors. So, we are coming from the top, the system is given, and then how we can realize the system, how we can implement that thing. So, this is called the top down approach. Now, another is the bottom up design. Now, in the top down approach already we have seen that we have started from the top, that as if that is the route which is given, that which system I have to design, and then I am partitioning and partitioning smaller and smaller subsystems until I get a realizable module. Now, this is totally reverse approach, that it starts at the leaves and puts pieces together to build up the design. So, it starts given a subsystem, given a system that I want to design, that as if we are starting from the leaf, and then subsystems are assembled to form a bigger subsystems, and when it stops when required functional specification is achieved. So, here what we are doing, that totally reverse concept, say as if what is available realizable module, say that small modules, say this is a some transistors, or it can be logic gates also, say I am taking this one, okay. This is a set. First these two are assembled, then say these are assembled, I am getting a bigger subsystem, Then again say from another I have got another bigger subsystem. So, these are some bigger subsystem. Now, again I am going up, say that I got the specification that I want to realize, means the behavior that I want to implement, that my function f. Okay. So, I stop here. So, actually here we are approaching from the bottom and stops when the behavior of the function is given. Now, what is the disadvantages of top down or bottom up design? So, there is no systematic procedure exist for decomposition. So, in case of top down approach, actually we are decomposing, and in case of bottom up we are assembling the, or we are assembling the smaller modules. So, when we will stop, actually there is no systematic procedure for this. It totally depends on the expertise of the designer. So, this is a very big disadvantage of top down or bottom up design. Now, which is better? Because all are modular design, top down or bottom up. One we are approaching from top, one we are approaching from the bottom. So, in practice that actually both top down and the bottom up design are used, they are needed. So, top down is normally used to divide and conquer to handle the complexity. Say if it is a bigger system, already I mentioned that to debugging is a big problem, that for a large system if it does not work correctly, then where is the fault, just to detect that thing, to identify the fault is a big problem. Rather, if we partition the full system and we take separately the each smaller modules and we check separately, then it will be easier to identify that where the fault is. So, normally another thing is that to design the smaller modules will be much more efficient, and obviously complexity will be much lesser if we handle only one smaller modules. And the bottom up is needed because in a well designed system the structure is influenced by what primitives are available. This is very important, because nowadays this what we are calling that available realizable module. So, nowadays this is called the library. One available library is there. What do we mean by library? So, library means that already some smaller modules, so that are actually designed and realized. Say if we take an example, say I have I am taking a two input AND gate, simple example I am thinking, two input AND gate and one 2 input OR gate. Okay. OR gate. Now, what we see that this is one, we can tell that this is one module normally often used, it is very much used in every design. So, this is my 4 inputs of the module, one smaller modules and one output. Okay. So, 2 input, 2 in and 1 out module. This is one module. Now, instead of designing every time these smaller modules, what we can do? We can design and test, and we make this is as a one module which has 2 input and 1 output, and this is the function, say F1, this I am telling this is one subsystem, one module. Now, once it is designed, we are telling that this F1 is a realizable available module. Now, say I have some library, say this I have some library is there. Now, library means already the pre-designed pre-tested modules are there. Say one is that F1 is there and its specification, already we have defined the specification of one system or subsystem. Say some F2 is available, similarly some F4 and up to Fn, same number of. Now, what we will be doing, that if now I want to design a system, then these are all my library is with me, that means all these F1 to Fn, these n number of modules are available, these are pre-designed and pre-tested modules. So, what I will be doing, that instead of designing from the scratch, I will just take from this thing from my library and I will put that thing as a block. So, that is why it is very much helpful. So, this that is why bottom up means that as if we are taking what is available, that library is available, what modules are already there, we are just selecting some modules and then we are assembling together to get a larger modules. So, that is why that both top down and bottom up designs are important. Now, we take a example of hierarchical design. This is a very common example of our computer system, digital computers. So, it has already we have seen the last day the same picture, that it is our memory and this is my CPU, and that instructions and data that are passing between memory and CPU, address lines are there. And see here this memory system, actually this we can take that as if this is a larger subsystem, because this full thing is a system, my digital computer is a system. So, it has now I am considering as if two subsystems, memory systems and CPU system. Now, again this memory system, this is a subsystem, this is partition, this can be viewed as if this is a combination of two other smaller subsystem, that is called the main memory and the cache memory. Disks are can be a third party, we will see later. Similarly, the CPU, this is a larger subsystem, and again if we partition this thing, that some smaller subsystems, this is a register file and ALU, the arithmetic logic unit. So, this is the very good example of the hierarchical design. So, now we see if we think that this is as a tree and computer is the root. Computer is the root means that I want to design a digital computer. So, this is my system. So, first it is partitioned. It is partitioned into two. This is my memory and this is my CPU. Now, this memory is a larger subsystem. So, it is partitioned into smaller subsystems. This is disk, main memory, cache memory. Similarly, the CPU I can think is a combination of two smaller subsystems, the arithmetic logic unit and the registers. So, we have some idea that how we can, so in this class what we will see that, or what we will read, that how we can design these smaller subsystems and then we will assemble, or the reverse thing also, top down approach, given a larger subsystem, how we can partition into smaller one, how it can be designed. So, we will learn in this class. So, now, another thing that is very important nowadays is the digital design process, and what is the current trend. So, all of we know that now the dimension, mainly the size of the circuits are changed enormously, and due to the advent of VLSI, that very large scale integration circuits. Because that means that within one smaller area, even the millions of logic gates, or you can think that millions of circuitry I can put. So, one thing is very clear, that it is almost impossible to design it manually, and that is why now the automation or the computer automation is needed. So, for that purposes, that this some computer aided design tools are introduced in the process due to its increased size and complexity. So, instead of doing manually, if we use these CAD tools and for the different levels, because if it is a that lower level, just now what I mentioned, that it is a say transistor level, or in the upper level it is a gate level, or even in the upper level it is a block level, means some of the gates are clustered to form a module. Then in every level, so what will be the flow, whether if it is a top down or if it is a bottom up, what will be the flow, that I want to discuss. So, designers want to standardize the design procedure, starting from the design idea to get the design implemented, the so called design flow. Now, new CAD tools are based on hardware description language to improve the process. Now, what do we mean by this hardware description language? Because so far we know that programming language, that we call that software languages, say our C, Pascal, C++, Java. Now, see here I want to design a circuit, a digital computer. See, my components are wire, that transistors, or if it is that some of the transistors I assemble, it will be a gate, one AND gate, one NAND gate. So, how we can specify that, as it is a tool, that computer tool means, say it is a software. So, I have to tell that tool or the software that this is the specification of the circuit, or this is if we consider the system, then we can tell that this is the specification of the system, means this behavior I want to realize. So, for that purposes, that some hardware description language, that means that as its name implies, that this is the language that will tell us that, see, these are the, this is a block that represents AND gate, this represents the flip flop, this is a wire, like that, this is a clock. So, this is the some language, HTL languages are proposed. Normally VHDL, Verilog, these are the different type of languages we use. Now, these HTLs provide formats for representing the outputs of various design steps. An HTL based design automata tool transforms for its HTL input into an HTL output, which contains more hardware information. So, these are just now what we told, that there are some design flow. Okay. We mark this line, this is very important, that what will be the design flow. Now, see, if we start that from the design idea, means the problem that I want to solve. So, this I am telling, this is my design idea. Then this is called some behavioral design. Behavioral design means, so first thing, what problem I want to solve or what system I want to design. So, the behavior of the design, that is clearly, that should be clearly told in this step. The first step should be that thing, that we are defining as a behavioral design. What will be the output? Then the outputs are flow graph or pseudo code, like that. Then this is a, from that behavioral stage, then some smaller blocks, some blocks we are partitioning. This is called the data path design. And what is the output? These are some bus and register structure. Later I am giving example of this thing. And then it is a logic design. So, this is again modular, that again I am partitioning into smaller blocks, and these blocks are now synthesized or realized by logic gates, and, or, not, etc. So, the outputs are gate wire list, or normally this is called the net list. This is called the net list. And now, these gates, I want that actually this is again it is partition, because one gate I can always realize by some transistors. So, this is we call the physical design. So, the output is transistor list, that means a set of transistors assembling together form a gate, and this we call that layout, means how they are placed in this set of transistors, how they are placed, that within the specific area. Say that my chip, what we normally we have seen that IC chip. So, there this is it is called that layout, how it is placed, how it is partitioned, what will be the size, this is called the layout. Now, it can be manufactured. So, this is some manufacturing stage, and ultimately we get our IC chip or board. So, these we can tell that this is our digital design flow. That means, if we summarize that starting from the design idea means that what system I want to design, say a digital computer or a digital calculator, that can be your design. So, first we will get the behavioral design, what will be the function, then data path design, that it will be some block diagram design that specifies, each block specifies some bus register structures. Then it is logic design, means that the same thing is realized by a number of gates and wires. Then again it is simplified, or it is realized by transistors, because ultimately the transistors I have to on a silicon, that IC chip, that is nothing but a piece of silicon. So, they are actually the transistors will be fabricated. So, then it will be manufactured and we get the digital IC. So, this is the digital design flow. Now, just now I that in the design flow, say the data path design, that once the behavioral design is unambiguously written or defined, then the using some bus and register structures we can take the data path design. So, see this is my data, and these are nothing but registers. Now, just we can think as if these are some storage. So, there are several storages are there and there are some interconnections. This is my main logic unit, and these are connected with the procedure for control of movement of data between registers and buses, means these are my control unit. So, this is the data path design, or what we call that bus and register structure. Now, another very important thing that we can think, that is the Y diagram. Okay. See, these were that as if that already we have discussed that the modular design approach, mainly the top down or the bottom up approach. Now, and parallelly when we I introduced the design flow, I told that the different type of definition, that behavioral or whether it is structural, whether it is in the physical, means that when it is realized by gate or transistors. So, that the different approaches and that to get the or to achieve the goal, to get the design to be implemented, that one Y diagram is normally defined. So, this is the my Y, this is my Y diagram. So, here this is a behavioral domain, that means the how many ways I can solve a problem. So, behavioral, that one say behavioral domain means already the way the system I have defined, this is the behavior. That behavior means that if these are my inputs, then this is the output. That means, if I1 is my input, O1 is my output. If I2 is the input, then O1, O2 is the output. So, in this way, that for a specific inputs, that what should be the, okay, this should be In, On. So, what should be the input output specification that clearly defines the behavioral domain. If it is given, then what we can do, that I can write that programs to get this behavior. So, I can get this thing. Okay, again that Y diagram I am telling. So, now once it is given, that means that program, again it is, then it comes to our that physical domain. It comes to this side, I am telling that this arm, as if this arm, there are 3 arms, and this arm is the that it is realized by transistors, then cells, and ultimately it comes to the that digital chip or the board. This we are calling the physical domain. Another is the structural domain, means the another arm that we are representing, we call that, given a system to be implemented, always that it is similarly the similar of the top down approach, that I can partition this thing into some smaller blocks or smaller modules, and this can be that some say adders, gates, registers. So, this is the structure. So, as if the structural domain, then from the adders, gates we come to this point, and obviously we know that adder, whether it is a adder, gate, register, decoder, any other functions, always that we can implement by a, or we can realize by a set of transistors. So, this is a very well known Y, we call that Y picture, the Y or Y structure, that for how we can use the, or how we can implement the digital design, how we can approach. Okay. So, behavioral representation. Now, how behavioral representation describes how a particular design should respond to a given set of inputs. So, mainly we are discussing about the CAD tools, because nowadays that just for its size, it is a huge number of circuits. So, how we can represent this behavior of a systems. So, behavior may be specified by Boolean equations, we will see later, we will read these Boolean equations. Then tables of inputs and output values, just now I have shown that behavior, always the behavior can be represented, that if this is the input, this will be the output. If I1 is the input, O2 is the I1 is the input, O1 is the output, I2 is the input, O2 is the output. So, this set of input and outputs clearly defines the behavior. Another way I can tell that algorithms written in standard high level computer language or in special hardware description language, or that one behavior easily I can described by computer language, which is nothing but some English type language. We know that software language, the C language is English type. So, using this computer language, always I can do that thing. Now, here one thing is very special, because here it is not software. I have to specify my circuit, the transistor, the gate, the decoder, the adder, multiplier. So, for that I need hardware description language, or we call HDL, instead of the software language. So, in this way that I can fit my behavioral representation to the CAD tool. Now, I take one example, then it will be clear what do we mean by behavioral representation. Say an n bit adder is constructed by cascading n 1 bit adders. What is adder? So, just I want to add nothing, but say n bit means, yesterday we have seen that that binary only 2 digit will use 0 or 1. Okay. Now, say it is a 4 bit, some 4 bit numbers I am taking. Okay. So, 4 bit numbers. We know that 12 means, our decimal 12 means it is actually 1 0 1 1 0 0, and say our decimal 10 is 1 0 1 0. So, this is the 2 4 bit numbers I want to add. This is I am calling that 2 4 bit adder. So, what I need? I need 4 1 bit adder. This is 1 bit, bit 1, this is 1 bit, this is 1 bit, and this is 1 bit. So, I have to add this 1 bit, I have to add this to 1 bit, I have to add this to 1 bit, I have to add this to 1 bit. That means that means a 4 bit adder, at a 4 bit adder. Okay. So, what I can tell, one 4 bit adder can be realized because it is hierarchical. So, 4 number of 1 bit adder. This is as a whole 2 4 bit numbers I want to add. This is 1 4 bit number, this is 1 4 bit number, and for that what I want actually 1 2 3 4 number of 1 bit adder. So, an n bit adder is constructed. So, if n equal to 4, I have given the example. So, for an n bit adder is constructed by cascading n 1 bit adders. Now, a 1 bit adder has 2 operand inputs A and B, a carry input C, a carry output CO, and a sum output S. What do we mean? Because see, now 1 bit adder I am considering 1 bit. That means, I want to add 0 and say 1. This is 1 bit to 1 bit. Now, what I want? So, these are the 2 operands. Now, if we add this thing, say I am getting 0 plus 1, say my sum is 1, currently we assume, and that say carry is 0. So, this is my sum, this is my sum. What is my carry? This I am telling the carry output is 0. Why carry output is needed? Because if it is for 1 bit, if it is for 2 bit, then I know that I have to add this thing and the carry will be added with the next bit. So, that carry output will be propagated. So, I need carry output. Now, when we are considering the sum of these 2 bits, see here it is 2 operands, another operand is actually there, that is my carry input, that is my carry input. So, this is illustrated in here, the 2 operand inputs A B, a carry input C, a carry output C O, a sum output S. So, the same thing, that if algorithm level description, say algorithmically we are telling stepwise, actually I am defining a module, say a module, and this is a carry module, this is a carry output, that means as if one subsystem I am defining, and these are the 3 inputs. Why 3 inputs? That input A B C, A B are the operands and C is the carry in. So, there are these are the 3 inputs, and then that these assigns some using, this is my behavior, that function, that how I can generate this carry output from here. So, if I see only the carry output, that means the way we have designed the digital system, that this is my carry module, or you can tell that this is my subsystem, that carry module. It has 3 inputs, these are my A and B, that I want to add, that from the previous one another C is coming, that is my carry in, this is my carry in, and only one output, that carry out. So, this is inputs, outputs, behavior, that this is a system. Now, that is a structural representation. So, structural representation specifies how components are interconnected to perform a certain function or achieve a designated behavior. In general, the description is a list of modules and their interconnects often called netlist. That as if I have a number of modules and there are some interconnections between them, specific interconnections that together form another larger module, and that gives the structural representation of the system. So, at the structural level, the levels of abstractions are the module level, the gate level and the switch level. The module level already we discussed, then it is module can be realized by gates, gates can be realized by transistors. Actually, in between I can write another transistors. Transistors can be mainly nothing but the switch. Actually, switch and transistor are same, the transistors are nothing but switch, not on or off. Now, pictorially if we see the same example, so this is my 4-bit adder, this is my 4-bit adder. This is a 4-bit adder. Now, it is partitioned into 4 1-bit adder. So, these are all this level, this is a all 1-bit adder. Now, 1-bit adder, what will be the components? So, there will be some, I have to realize a carry, I have to realize a sum. So, one carry output and one sum. So, for each one it is same, that carry and sum. So, in this way I can say a 4-bit adder I can hierarchically I can implement. And another thing you just notice, see here the all carry and sums, that modules are similar structure. So, these what we mentioned, that this is the duplicate of modules, and in digital design mainly this is the advantage, that same type of one large systems can be realized by a similar modules, and it is very important, or it is very advantageous to fabricate the similar modules in a smaller area. That what we call that VLSI or simple ICs also. Now, the last step, that physical representation, means that in an IC process the lowest level of physical specification is the photomask information. Means that physical representation means that the full system, it is partitioned into blocks, then it is realized by gate, then it is realized by transistors, and now that we are using the CAD tools, means all the things are automated. This is digital automation. So, just to get a IC, a digital IC, that in the fab lab we have to send the photomask information, means that which transistors will be fabricated on the silicon and how. This is nothing but a photomask information. So, this is required by the various processing steps in the fabrication process. Now, at the module level, the physical layout for the 4-bit adder, the example I have given, may be defined by a rectangle or polygon that specifies the outer boundary of all the geometry for the adder. Because actually if I want to design a 4-bit adder, that is nothing but a, when we will see, this is a piece of silicon, say a rectangle silicon piece. Then when the 4-bit adder, now 4-bit adder means that a set of transistors. So, in the 4-bit piece of silicon, on the piece of silicon, that how the transistors are fabricated and where, what will be the placing, mainly that is the, that information is the photomask information, and this is the set of sub modules and collection of ports, mainly that information we have to send to the fab. So, now the main thing, that if I want to summarize, that main thing what is there, that given a digital system, that or if my aim is to implement a digital design, that starting from the problem, that how I get the actual realization by transistors, and then how it is fabricated to a IC. This full thing, starting from the design problem to from the IC, this we are telling that design flow. Mainly for this design flow, because for the size and complexity of the current digital designs, we are using the CAD tools, and this is called the design flow. So, pictorially we can just again we can summarize. See that these are my design idea. So, first we start with the, this is called the design entry. This is my design entry. So, for that what we need? We need one hardware description language. Normally VHDL or Verilog, that is the VHDL or Verilog is needed. Okay, if we start writing, then from the design entry, that for this design entry, say Verilog or VHDL, means these are my HDL. this is the HDL that is needed, hardware description language, some programming. Now, from there I got my net list, that means the how the gates are connected. So, the gates and the connection between the gates, also it can be not gate, it can be a module also, that means some modules and the interconnections. So, net list we are defining so net list. Now, I know I want net list means that is some modules and interconnections. And then it is these are we call the logical design, this is the logical design, and then again it is partitioned into some smaller blocks, and these actually the chip, these I am telling that this is my chip, and again from this chip this is some actually in the chip the smaller blocks are there that or smaller modules are there, and from there actually the logic cells are here. So, this we are calling our physical design. So, this is my physical design. Up to this is physical design, and this is my logical design. This is my logical design. So, this is the overall introduction of our digital system design course. So, next step we will start the course. Today we will start discussing on digital logic part 1, but before that I want to revisit a quick summary of the previous 2 lectures. Mainly the previous 2 lectures I gave an introduction of digital system design. What do we mean by the digital design? So, starting from the design idea that if I want the digital ICs, so first it should be the behavioral description, means that given the problem how I describe the behavior of my problem. Normally nowadays the CAD tools are used for that purposes.